Hey guys, welcome to the ACM meeting. Today we're going to be having a workshop on deep learning. If you want to follow along with the code, we do expect that you have Anacondas installed. It's a package manager for Python. It does take a little while to install, so if you haven't done that, you should probably do that now. Without further ado, I'm going to introduce Jonathan. He is our speaker for today. He's getting a Master's of Science in Computer Science at FIU right now, and he has a passion for deep learning, and he's been doing this in his free time and just wants to show you the implications and what you can do with deep learning techniques.
So when you want to start? Right now? All right. So my name is Jonathan Beltran, and today I'll be presenting deep learning. So there are many parts to deep learning. There are many things that can be solved. We're going to be looking at convolutional neural networks, and we're going to be doing image recognition. So deep learning became popular back in 2012. There was a model that was presented called AlexNet that beat all the other classifiers by a good percentage. They got 20% error on their thing. The ImageNet is a challenge where you have to classify 1,000 objects in 10 million images. And it started in 2009, and so previously everyone was getting like 35% error, 25% error, and then these guys came and they got 18% error. Prior to the competition, neural networks weren't really a thing. They were very unpopular, and they would take very long time to solve problems. And now they're being used for language translation, both textual and voice language translation. Google's new headphones are using neural networks to translate languages as it hears it. So AlexNet presented what was the first deep learning algorithm. They were using GPUs to make their neural networks train faster. And what I mean by this is that you have your traditional neural network over there, which is a single hidden layer and outputs. A deep neural network will have multiple hidden layers. And so they were trying to go deeper instead of wider. Instead of trying to increase how many nodes are going to activate, you increase the amount of layers that need to activate. This is the data set that we're going to be using. It's called CIFAR. It was made by the same people who made AlexNet. It's 10 objects in 60,000 images, and each object will have 6,000 examples. So this is called LENet. This is the neural network that was built in the 90s that was never successful because it took too long to run. So this is what a convolutional neural network is. A convolution is a transformation where you take a filter across the picture, and then you make a new. So a convolution is a filter that you take across an image, and then you produce this new matrix, which is just the sum of the weights. Yeah. And so these are examples of convolutions on images. So kind of small. If we look at the top right, on the two top right ones, you'll see that it's learning how to identify lines and shapes in an image. And this is just a layer 2 convolution, so it's pretty early on. But then when we look at convolutions at the last layer, we can see that it learns faces. Like if we look at the middle section with that woman there, we can see that it's mapped out her face as a function. And so it learns how to identify her. And so after each convolution, we do a subsampling. This is also called pooling. And what we do is we take the max value from the convolution, and then we make a smaller image. The reason we want to do this is because we don't want to lose the information of the picture. We basically want a summary of what the picture looks like to learn about the lines and shapes. And then after you've done your convolutions and subsamplings, you go for a fully connected layer, which is the traditional neural network where you've taken your inputs, the inputs activate, and then it'll identify a class of the image. So in this data set, our fully connected layer will be outputting to a layer of 10 images because we have 10 objects we want to identify. And I think I already said all these things. So now we're going to be moving on to the actual implementation. This is the repo that I have the code on. Is it one word? Leave that. I'll show it in the next slide, but this is the repo, and then we're gonna be. I'm gonna give you guys time to install this, but you want to go to this link and you want to download Anaconda. This is Python. How many of you guys already have it installed? How many of you guys are installing it right now? Okay. I have an environment file. Yeah. You can get Anaconda Mini. Oh, this. Oh, I'm not gonna be. This is just my camera. It's gonna be bigger when I. So, to those of you who already have it installed, then did you get the repo yet? You.
Is there anyone who's lost and needs help?
So, to those who want to join along that just came in, I'm going to need you to download the Anaconda package if you want to code along with me. And then this is where the code's being hosted. And so I'm going to start with the coding part of the workshop. So this first snippet is going to download the dataset. That should take a little bit. So, like I said before, the dataset that we're going to be looking at is 10 objects and 60,000 images. Each image is 32 by 32. Okay. GPWriter, it's on the README of the GitHub. Should be. In case it's not, that's the command. Was it there? Yeah. All right, so I got the data set. All right, so these are the libraries we're going to be using. NumPy is a Python library that's used for matrix operations, and then Pandas is used for data frame storage. Matplotlib is what I'll be using to print out the graphs. And then, of course, this workshop's about TensorFlow. So when trying to identify images, color doesn't really matter, right? If I want to identify a car, I don't care if the car is red or blue. So I'm going to take the data set and I'm going to remove the colors by making it grayscale. Another thing is that neural networks don't know how to predict what a car is. The only thing that it learns is functions. So we're going to take each one of our images and we're going to label them as vectors. In this case, in this example, we have an input A, and the way the label will look like is this vector where there's a 1 in A's position. This is called OnePoint Encoding. So then, how do we calculate how far off our prediction was? So there's something called categorical cross-entropy, and it'll just take the highest value and make it a 1. So that's how we'll be able to tell whether we predicted right or wrong. The network is going to produce this y hat, and we're going to check it against every label. And so traditionally in neural networks, you make a prediction, you get some error, and then you do gradient descent to check which direction you should go to fix the weights so that you can reduce your error. But this isn't feasible with images. These are very large input sizes, and you have to do it on all the data. So then there was this new concept introduced called stochastic gradient descent. We're going to do gradient descent on only part of the data. We're going to guess the right direction to move in, and then that's how we'll find out how we're doing. But it doesn't work as well as gradient descent. The steps that we're making are very small. So what we do is we make multiple steps until we reach the minimum error. So then now we're going to write So now, how do we normalize our image? The image is a 3-color channel. It has red, blue, and green, and each one is the value between 0 and 255. So with NumPy, the way you can normalize an image is we want to take every value and divide it by the max. And so in NumPy, it's going to take this divisor, it's going to divide everything in the matrix by 255. For doing the one-hot encoding, we're going to be using a library. I have it here. sklearn has implemented one-hot encoding through label binaryizer. And so what we're doing here is we're preparing our data by pre-processing. And we have 10 objects that we're trying to predict. So we're going to take each label, which is a string value, and we're going to make it into a vector. Now, I'm going to be taking our data set, I'm going to load it into memory, and then I'm going to be performing the pre-processing steps on it. You can just run this next one. So when you're doing this type of programming, it's usually that you have a GPU and it's very limited in the amount of size in memory. So what you can do to overcome that is use batching. So we're going to take our images and we can say that we're going to train on 64 images at a time. Oh, I have. This is going to take a little while. Well, we'll know it's done when this is white again. All right, so now that we've made our images grayscale and we've also fixed our labels, we're going to load them back into memory. Forgot to get rid of that. So then now we're gonna actually code some stuff. So TensorFlow has several libraries. We're gonna be using these variables down here. Whenever you want to store an object, you make it a placeholder. So you do tf.placeholder. If you're storing an integer, it would be tf.int32. If it's a float, it's float32. You put the shape of the integer, which is going to be like the matrix size. If it's a 3D-dimensional matrix, you would put 3, 3. And then you can give each tensor object a name. tf.variable is just can hold anything. tf.zeros is when you want to make a matrix of all zeros. tf.truncated normal is when you want to make a matrix with a normal random distribution. And now we have the things that we have convolutional 2D. So we have 2D images, so we have to do a 2D convolution. We have the maxpol library. So I guess one thing I did forget to mention is that after you do all your convolutions, the last layer is a fully connected layer. But before you can get to there, you want to flatten all your data. So you turn your 4D convolution into a 2D data, and then you can do the fully connected layers. So what did you want to see? Oh, yeah. So one thing I'll talk about now is that neural networks are very good at learning functions. Sometimes they can overlearn them. We don't want the neural networks to learn about these images. We want them to be able to recognize all types of images. So one technique that they use is called dropout. So what they'll do is that while the network is training, there'll be certain things that it learns how to activate, like it'll learn how to recognize your face. But we don't, if we wanted it to recognize all types of human faces, we might not want it to recognize specifically your face, but any human face. So what we'll do is we'll randomly turn off parts of the network that would regularly activate, and then have the neural network try to learn anyways. This will reduce it so that it'll learn shapes, but it won't learn specific images. So then now I'm going to create the placeholders for our objects. We're going to need a placeholder for our images. We'll need a placeholder for our labels, and then we'll need a placeholder for the dropout. So you could specify to TensorFlow how many of these data you want to keep by giving it a probability of how much it should keep. And then now we're going to do the convolution. So I put none here, but we're going to have to put the sizes. So a convolution is an input image. It takes in a filter to go over it. The filter has a size and how fast it moves. And there's a concept called padding where when you go over the image, if the image is of odd number, should you keep the, when you're doing the filtering, you're going to go over one, right? If the filter is not exactly divisible by the dimension, it's going to go over. And so you can either tell it to fill it with zeros with same counting, or valid by keeping it truncated. And then each convolution is passed through an activation function, which I'll talk about later on. So we want our weights to match the size of the filter. So I'm going to take the dimensions of my filter, which is this. So the filter is it's an array of two integers. It specifies the length and width of the filter. So k size 0, k size 1 will have the size of the filter. We want to copy the amount of how deep the image is. So with the initial image, it's going to be 3 deep because there's 3 colors, right? There's a red, blue, and green in an image, and so when I get that from the shape, the color channel is always put last. And then so the convolution is a transformation from one color space into another. The initial image is a 3-color image that comes in, but what comes out is how large we want it to be. The main idea here is that we'll keep reducing the images in half, but we'll increase how deep the convolutions become. The deeper the convolutions, the more complex functions you can learn. And so here I call it weights. It's also known as a filter. I'm going to initialize the filter to be a random distribution with 0 mean and 0.1 standard deviation. So this is optional, but to every tensor activation, you can add a bias to it, and the bias is just going to have to be the same size as the filter. So then you take the image, you apply the filter onto it, you specify how fast the filter is going to move with strides, and then the padding. And then you add your bias to the tensor, and then you pass it to the activation function. For max pulling, it's you just put the image, how fast you want it to go across, and then the padding. For the last layer, we're going to be doing a regular neural network type of thing. We're just going to be taking the output multiplied by the weight, add to the bias, and then return that. That's going to give us the last vector, the vector that has 10 inputs inside of it. So we're going to be implementing the VG19. So this is LENet, and we're going to be doing an even deeper one. It's going to be 13 layers, 19 layers. So then the activation function we're using is called rectified linear units. Whenever the activation is positive, we'll get a positive result, and whenever it's negative, we'll just return 0. The reason we're doing this is because to use the regular sigmoid function, which can go positive and negative, it's too expensive to calculate. It's much faster to do this. And also, our output might look something like this on the left, but we want it to be a percentage about how much we're confident a certain object is. So we'll be passing it through a softmax function that'll transform the vector on the left to the vector on the right. So in the model I talked about before, the VG19, they use a convolutional size of 3, and they copy the entire image over. So when you do a stride of 1, you're going to copy each bit from the image and just transform it with the weights. And then what they do is instead, on the pulling layer, they cut the image in half, but they also make it twice as deep. So they'll copy an image of the exact size, and then when they do the subsampling, they're going to make it deeper. So then we'll do the first convolution. Our input is going to be x, which is going to be the image. Our filter size, since we're taking in 32 by 32 images, our filter size is going to be the same as the image. Our case size, which we said was our convolutional filter size. How fast we move across the image, and I'm going to be using the same padding. You can also put valid padding if you wanted to. And like I mentioned before, we're going to be using the vector linear function as our activation function. So following this model, what we do first is we take a convolution on the image, and then we do some subsampling. So after I do my convolution, I'm going to take a max pool. I'm going to pass in the convolution I just calculated. The size of this, the size that I'm going to take is the same I have here. So right now, is anyone lost? Does anyone need some? Does anyone have any questions? So now we're just gonna do this. Oh yeah. Right. And there's actually many ways of subsampling. I'm going to be doing max filling here. You can do an average of the numbers inside your filter size. You can do a lot of things. So then we just keep doing this as deep as we want. So we're going to take in the subsampling as our next convolution. So I recently read a paper where it says that the deeper you go, the better it is. And like I said before, after every subsampling, we're gonna go deeper because we want to learn about the complex functions. And so just to run this really quickly, I'm gonna be copying this model exactly. So this one says that there's 2 convolutions followed by 2 subsamplings and then connected to a fully connected layer. So we're gonna have to flatten our tensor. So that we can connect it to a fully connected layer. The convolution produces a 4-dimensional object. Flatten will make it 2-dimensional so that we can apply regular neural network techniques to train off of it. And I think they have 2 fully connected layers. Yeah. So then, a fully connected layer is a layer of however large you want to make it. Usually they use powers of 2 to specify it. It could be 10, it could be 5 to 12. It's a parameter that you can play with. So I'm saying that actually, so let's try this. So the output of the last one is going to be 128. So then I'm going to make a fully connected layer that has the next ties. And then we're going to get our output after this. So after the fully connected layers, we're going to do our dropout so that we can turn off some parts of the network at random. And just to make sure everyone's still with me, it's the same dropout that I talked about here, where some function is going to activate, but I don't want it to learn strictly the image. I want to learn about the shapes in the images. And this, and so our output layer is supposed to predict one of the 10 type of classes that we're trying to predict. So this is how many. This is how much I want the last layer to produce. And I want to return. This is the model that we're going to be using. So you can have as many fully connected layers as you want. You can have as many convolutions as you want. The thing about the fully connected layers is that they take the longest to calculate, and you can have it's another parameter that you get to play with. So convolution neural networks and deep learning has a lot of parameters involved, and the way you improve your models is by changing the variables. Yeah. So then down here, I just have what we wrote before. This was the placeholder for the image. This was the placeholder for the labels. This is a call to this function that I just made. And so I'm going to give the logits a name so that if I ever save the model and I want to pull back one of my variables to see how well I did, I can call it by its name. So then I talked about how when we make a prediction, we're going to get a value like this. So I'm going to pass it through a softback function so I can get a value of probabilities. And then I'm going to be taking the mean of how well I predicted. And then I'm going to be passing that through the stochastic gradient descent. Atom optimizer is a specific implementation of stochastic gradient descent. How well I did is if I get the one value from each of the vectors, they should line up. So if y hat produces this as its 1 and y is this, then it'll return as I predicted it correctly. And this is the atom optimizer algorithm. I think I called it filter size with an underscore. Yeah. This is shrub. All right. So now we're going to train the neural network on the values we just gave it. And we're going to print out how well we do after each iteration. Yeah. So epochs are the amount of times we're going to pass the entire data set through the neural network. The batch size is how many images we're going to be training at a time, and then this is our probability of turning on or off an activation. You can play around with these variables. I'm going to be using these for now, and then this is going to train the data set right now. Okay. So this is going to take a little while, so I'm going to be taking a break. You can go ahead and grab some pizza over there if you want while this is running.
When you go grab the pizza, if you haven't signed in, please sign in with the cheat that Krista has in the hands. By the way, Gio, we got the flight controller for you for the drone workshop. So yeah, just come up to me.
Okay. Okay. Yeah, this one finished. Okay, so this one finished training. It ended up around the same. So what this means to me is that the model's not complex enough to learn even further. So now we're going to try the other model out. In VG19, you have 19 convolutions. They start to, in their model, they start to stack convolutions on top of each other. They do this so that they can create even more complex shapes. I'm also going to increase how much the last layer is going to learn on. All right. So now I'm going to leave it running with a more complicated model, the VG19. And so you guys give up? Oh, what was wrong with it? Or, yeah. Okay. So did anyone else have any troubles? You okay? Is it running on your computer? What happened? Yeah, oh, it is already. Oh. Yeah. All right. So this code is a test bed. You can play around with all the parameters. You can try different models that you can find online and implement them here. But basically, the idea behind convolution neural networks is that you take the image, you train the filters so that when it recognizes a certain image, it'll activate. When it activates, then you can say that this image is one of, like, for example, it's an airplane. Or the most important thing to take out of this is that you apply convolution, you summarize the values of the convolutions, and then you connect your summary to a fully connected layer, and the fully connected layer learns how to identify the images. So then the consequence of this is that since it's the fully connected layers that are predicting the images, if you want to predict new types of images, you don't have to retrain the entire network. You just have to retrain the fully connected layer. So that's the advantage to this architecture. Yeah. So let's say this data set learned how to identify 10 objects. You want to do 11 objects now. You don't have to rerun this. You just have to train the last layer. Yeah, so Tensorflow already does it for you through this through that line. So this is the stochastic gradient descent that I was talking about, where it takes multiple steps to find the correct loss function instead of trying to calculate the real one. Yeah. You can play around with that too if you want. I just chose this one for this presentation. So that's going to be about it. If any of you are going to stick around, I can help you out with your errors.